Hi, my name is Fred Gucci, and I will present my master's degree dissertation on the emergence of an information bottleneck theory of deep learning. Here's our agenda. I will start by introducing the problem, objectives, and methodology. I will then give some background on machine learning theory and information theoretic machine learning, comparing both. I will then spend most of the time talking about the information bottleneck theory itself, the original information bottleneck method, IBT main thesis, and the criticism it received. I will follow on with Stefano Suate's work on the bottleneck and representation learning. Then finally, I will present deep learning phenomena in this new narrative. To conclude, I will present this theory strengths, weaknesses, and research opportunities. So let's talk about the problem. There seems to be some consensus that the practice of deep learning has outpaced its theory. So, and here IBT may present a new perspective to fill this gap. But to the extent of our knowledge, there is no comprehensive digest of IBT and how it compares with the current learning theory. So our objective is to investigate to what extent can it help us understand deep learning generalization and build this digest. For that, I used some research questions to guide the work. Some of them regards the theory fundamentals and how it compares with the current one. For those, the methodology that I used was to start from the most basic axioms and build from the ground up machine learning theory and information bottleneck theory. And then I was able to compare not only their assumptions, but also their choices along the way. Another set of questions relate to the current state of IBT and its application to deep learning. The methodology for those was to start from a primary literature and start mapping topics, finding gaps, and look for more literature as needed. So, current machine learning theory sees learning as a searching inside an hypothesis space. So we want to find, during training, a function that will generalize well for new examples in the future. It's an optimization problem. In the information theoretic perspective, learning is a communication problem. So let us imagine there is some truth, some law of nature that we want to learn. We can see that as a conversation with nature. Nature has sent us a theorem encoded in the observations for us to decode. And our understanding, encoded in a language familiar to other agents, is a theory that can be tested and be useful to predict future observations. So let's take, for example, the true relationship among the sides of a right-angled triangle. The Babylonians observed this relationship in many instances and encoded them in tablets. So to know the size of the hypotenuse in a new triangle, they would look up a similar case in their engraved tablets. And so their theory, this encoding, had a rate, a number of bits it's used, that was quite large because it memorized several previous examples. And also it had a distortion, which is inevitable, as there is no way to engrave all triangle examples. Later, in the same conversation with nature, the Greeks resumed all their understanding in a much simpler function that required less bits to encode, and which had a much smaller distortion. Actually, for measurements in the plane, the Pythagorean relation presents no distortion at all. So, in fact, this is also an optimization problem, where we want to find the encoding of the observations in its simplest form. subject to keep the distortion within a tolerance level. In the first part of the dissertation, I built these learning perspectives genealogies. So from the most basic definition of intelligence, I showed the need for language and how different concepts of knowledge define different languages. I showed also that machine learning is based on Bayesian inference, a language that is different from other computer science fields which use logic as a language. And I also showed that both machine learning theory and information theory share the same genealogy. Both fields, in both fields, the unknown distribution is fixed. There is no time concept. They are both optimization problems, as I already said. They are agnostic to loss metric, a point that I will return later. And they have also their difference. But there are more choices than unconsiderable differences. So while current theory is hypothesis space dependent but task independent, the information theoretic learning is task dependent and hypothesis space independent. And if in machine learning theory we can use continuous random variables, possibly infinite input and target space, and the unknown distribution can be deterministic or stochastic. In information theoretic learning, the random variables are discrete and the input and target spaces are finite. And also, the distribution must be stochastic. But as I showed in chapter 6 of my dissertation, this is hardly a problem if we consider that what we want is models that will run in computers that are finite. And some discretization will happen anyway. So instead of apples and oranges, they look more like different sides of the same coin. And to sum up, they share most assumptions. Their differences are conciliable choice, and you can build bridges between these fields as minimum description length method has shown. So what is the point? Why bother? Are information theoretic learning methods just pedagogical tools, as David McKay has said? Are they redundant? I don't believe so. I think it's important because they are different narratives capable of different analogies and new connections. So let's talk about the information bottleneck theory. And I will start with the original method. So let's see this learning problem setting that we were talking about. Tishby et al. Point out that an arbitrary distortion function, is an arbitrary feature selection because it defines what is kept and what is not kept in the representation. But they also notice that there is commonly a target variable that represents what we want to learn, which is orders of magnitude smaller than the input. This variable is the task. So a good representation will keep the information needed for this task while forgetting the information that is not about the task. And a representation can be good for deciding if, for example, this input image is a cat or dog, while being terrible for labeling the breed of the cat. So relevance is task dependent. The information bottleneck principle gives us the Kullback-Leibler divergence as the canonical distortion measure, because it is equivalent to the amount of information of y presented in the input, but not captured by the representation z. The information bottleneck Lagrangian is a method to find minimal sufficient statistics, that is, good representations of the data, and is widely used in information theory. So Tisch noticed that his information bottleneck method could help explain deep neural networks by treating each layer as a random variable. And it would also allow us to analyze what happens during training in information theoretic terms. And his experiments results were astonishing because they showed a clear phase transition during training. There is a rapid fitting phase where the information grows in all layers, and then a slow compression phase where most information is forgotten. So information bottleneck theory main thesis is that learning is forgetting. These were extraordinary claims, but extraordinary claims demand great data. And there was a wave of criticism to IBT's seminal papers. Saxe et al. And others challenged the experimental setup in many ways and were also not convinced by the theory. Even Tischby agreed about the lack of rigor, while still complaining that they were throwing the baby with the bathwater. But some criticism was actually due to missing or not explained assumptions that are different from the current theory, and some we have already addressed. But there was more. How can you talk about stochasticity after training when the weights are already set? From where comes the pressure for reduced information in the activations? It was not well explained. In parallel, Professor Suato's team at UCLA developed an extensive body of work. They addressed the problem of where does the pressure for lowering the information in the activations come from. They explains the emergence of generalization disentanglement in deep learning, shows the role of noise, and also proposes a variational method for estimating mutual information, a point of much debate in the criticism. And also they relate their theoretical findings with pack bias, among many other things. Let us show this progress. Starting from defining the best representation possible in information theoretic ways. So we want our representations to be sufficient, meaning that we want that it keeps all the signal, the information about the target variable that is encoded in the input. We also want it to be invariant to noise, to not keep noise at all, to not correlate with any noise in the data set. We want it to be minimal. And one of the results was that to show that a minimal representation is also maximally invariant and vice versa. Also, we want disentangled components. That is, we want that the representation to be composed of components that are independent from each other. So then they formulated a variational problem to find solutions with these characteristics. So, and this optimization problem generates minimally sufficient disentangled representations. To solve the optimization, they also used the Lagrangian relaxation, and they arrived at information bottleneck form solution, and that is very similar to Tishib's one. Most of the time, we only focus on minimality and sufficiency, and forget the disentangled term. But Achille noticed the problem with this activations information bottleneck, because it's incomputable. Z is a representation of future data. So how can you compute with data that you don't have? And if we were talking about compressing the information in the activations during training, memorization of the index would be a valid minimization. And so there is a problem here. But let us keep this problem, that we'll come back to it later. So they decided to study cross-entropy under the information bottleneck lens. A problem that Zhang et al. Showed is an apparent paradox that because deep neural networks can fit random labels, and yet they generalize. So generalization in deep learning is a matter of not overfitting. Achille and Soato decomposed the cross-entropy loss, assuming that the input data is sampled from a generative model parameterized by a true theta. And this allowed them to notice that only one term in this decomposition is negative. And this term relates to the information kept from the dataset that is not explained by the true theta. So it refers to memorization of noise in the dataset. And being the only negative term, the optimizer will tend to increase it. So that may explain the deep learning tendency to overfit. A naive solution would be to neutralize this term by adding it back to the loss. But this term is impossible to compute because we don't know theta. At least we can upper bound it. Surprisingly, they arrived in a new information bottleneck Lagrangian with a different meaning from that one from Tishib's bottleneck, which is called the weights information bottleneck, or information in the weights. This weights information bottleneck limits the information in the training. So while the activations IB limits information in future examples, in future data. So we can explain the pressure to reduce information in the weights, but we still can't explain where comes the pressure to reduce the information in the activations. Maybe these different information measures relate to each other, and this will help. And actually, they do. They showed that the information in the weights upper bounds the information in the activations. And this information in the weights, despite being itself challenging to compute, it can, in its turn, also be upper bounded by future information. So now they showed how future behavior is defined by what happened during training. So they showed how you have representations of examples of future data that are small. Where does this pressure comes from? So now we can talk about what interests us, deep learning. Up to this point, IBT learning is just an idea. And how does it compare? How does it relate with deep learning? So deep learning is about layered architectures, but also SGD as an optimizer, large data sets, and a loss function. That is standard practice, be the cross entropy. But there is no information regularizer there. And there are many ways to reduce information in the weights. You can explicitly use a regularizer, as in the information dropout paper. It can be imposed by architecture, not only by the layers, but also by max pooling, the noise in dropout. Anyway, once again, Zhang et al. Showed that generalization happens even in the absence of regularizers. So, can layers alone explain the pressure to reduce information in deep learning? And there's no need. So here's the last piece of the puzzle. Another remarkable result from Aswato's student is that SGD performs variational inference with an implicit loss that is different from the loss that we put in the model. And this implicit loss has an information regularized term. So even if we don't add a regularizer to compress information, SGD puts one there for us. And now that we connected all the dots that sustain the IBT narrative, we can use it to explain deep learning phenomena. So generalization, despite a huge expressiveness of deep neural networks, the point here is that is information in the weights that is and not the number of parameters that is the effective capacity measure. And this relates to the information theory difference of data and information. We also talked about how disentangled representations happen, why there is this bias towards disentanglement. So to recap, SGD inserts an implicit regularizer that pressures a reduction in information in the weights. This information that is reduced is an upper limit to the information in the activations and the total correlation. So when we reduce the information, we are also disentangling the representations. Another phenomenon is the scarcity of sharp minima in SGD optimization. Once again, SGD forces a reduction in information in the weights, and this is the same as lowering the Fisher information in the weights. And the geometric meaning of the Fisher information is the curvature of the loss. So when we reduce information, we are actually moving to regions of the loss of flatter minima. Another very interesting phenomenon is the critical learning period that can be observed in animals and deep neural networks. So the classic experiment showed that cats with a vision deficit during early development have a permanent skill impairment, even with biologically perfect eyes. And the same permanent skill impairment was seen in deep neural networks, where the input images were blurred in the first training epochs. So why does this happen? This happens due to the phase transition that we talked about. Their experiment noticed that the more prolonged the sensory deficit, the higher is the information in the weights. This means that the deficit makes the network memorize more in search of good performance. And also, when the phase transition happens and the network starts squeezing, there is much more information to compress. And in geometric terms, you can see that when you used a lot of information, you went to regions of sharper minima. And when the phase transition happened, you were stuck, imprisoned in a sharp minima region. And this explains the critical learning period, not only in deep neural networks, but also in animals. So let us conclude. IBT biggest strength is its narrative that connects seemingly unrelated phenomena and practice. It allows us to analyze the training using information. And its biggest weakness is the lack of rigor. It has improved, but is still a problem. The discredit is hardly being unjustified, but I believe that an emergent theory deserves some slack, and fragmentation is still a problem, which I hope this dissertation can be of some help. I think there is much research opportunity in building the theory. There's much to be done. It is possible to reformulate PAC using beta to unify epsilon and delta. And I think that Alemi has worked on beta-based PAC, but I am unsure. I also believe that there is room for new optimization strategies that take advantage of different properties of the training phases, probably bringing more ideas from statistical mechanics. And another area that I see opportunity is in transfer learning. You can build topologies of learning tasks based on information in the weights. And I believe that Suato's team has shifted focus to transfer learning as well. So, to conclude, to sum up, I believe that information bottleneck theory is still emerging. It's not complete. It still lacks rigor, but it already presents a compelling narrative with exciting results and many open opportunities.